I'm here with my friend and fellow geek, Chris Scanlon. And we're going to talk about decibels. In audio, decibels are a unit we use to help quantify how much sound pressure, sometimes we refer to that as SPL, we experience. Decibels can also be used to measure other forces, like power, and sometimes we see the symbol appended as dBm, dBV, or dBu. But for audio, it's just plain old dB. Decibels are not measured in the same way we measure most other things. They're a ratio, and it's based on a logarithmic calculation. A friend of mine who's a mathematician once told me, logarithmic calculations were invented to make smart people feel dumb. And boy, does it work. Luckily, I never liked math anyway, so it's easy not to like logarithmic calculations any less. In fact, I'm kind of intrigued by them, so we'll play with a few of them a little bit later on.
When we think of our traditional measurement, like length or speed, we can note the difference from a decibel. For example, if we're driving 10 miles per hour and increase our speed to 20 miles per hour, we're driving twice as fast. If we increase our SPL from 10 dB to 20 dB, it's twice as loud. So far, so good. If we increase our speed from 20 miles per hour to 30 miles per hour, we've increased our speed by an additional 50%. If we increase our SPL from 20 dB to 30 dB, it's twice as loud. Whoa! Every 10 dB, we double or half depending on if we're going up or down. Therefore, 90 dB is twice as loud as 80 dB. That's the magic of a logarithmic unit.
How do we make decibels? Well, in the pro audio world, we convert electrical energy to acoustic energy using transducers. Hey, I'm allowed to use words like that. This is the Geek Boot Camp after all. A transducer is a device that converts one form of power to another. In audio, they come in many forms. These include microphones, phono cartridges, and of course, loudspeakers. Remember earlier we talked about coils, and magnets for motors, and loudspeakers. When a loudspeaker, the electrical energy creates a magnetic field in a coil, which causes it to react with a permanent magnet. This causes the cone to move, pushing air and making sound waves. As we convert the electrical power into acoustic energy, we'll note a few more calculations.
As we double the amplifier's power, we don't just get double the loudness. In fact, we only get an increase of 3 dB. Loudspeaker rating measurements are often taken powered by 1 watt from the distance of 1 meter. Increasing the power to 2 watts will increase the decibels by 3. From 2 watts to 4 watts, only another 3 dB. From 100 watts to 200 watts, just another 3 decibels. From 1,000 watts to 2,000 watts, it's only another 3 dB.
Wait a minute. Does that mean I can get the same increase from 1,000 watts as you can from 1 watt?
Yeah. It takes increasing amount of power to produce more sound as the decibel levels increase.
Well, that hardly sounds fair, but I guess it's not the first thing in life I'd figure is unfair. In fact, physics does us a little return favor, though. Check it out. As we measure how many decibels we lose over distance, we'll see. Taking our 1 meter measurement as the benchmark, we find out that every time we double the distance, we lose 6 decibels, or the equivalent to 4 times the power. So, from 1 meter to 2, we lose 6 dB. From 2 meters to 4, another 6 dB. But from 20 meters to 40 meters, just 6 dB. Now, these rules apply to point source devices, like most loudspeakers, but in the interest of fairness, it doesn't apply to line arrays. They behave differently, and they come with their own set of inherent complexities. They could be a DVD all of their own.
So we know what we gain from power and what we lose from distance. But how do we figure it out when planning for events or reading specifications? You could figure this out the long, hard way, or we could use some quick, relatively painless formulas.
To calculate the increase from power, we can simply take the log of the wattage times 10, like this formula. For example, if we have 1,000 watts, we take the log of 1,000, which is 3, times 10. Therefore, we know that going from 1 watt to 1,000 watts will give us a gain of 30 decibels. Likewise, we have a logarithmic calculation for determining loss over distance. If 10 times the log gives us a 3 dB gain, 20 times the log of the distance must give us a 6 dB loss, right? Right. Let's do it with the basics first. We know that increasing distance from 1 meter to 2 meters means a loss of 6 dB. The log of 2 is approximately 0.3 times 20 equals 6. Cool, huh? So at a distance of 15 meters, the sound pressure level will be 23.5 dB less than it was at 1 meter. Here's a slick little formula that even shows it as a negative value.
If you don't much care for calculators, there's an app for that. There are many online calculators or smartphone apps you can use to figure these things out for you. There are several devices we can measure decibels with, including commercially produced SPL meters with built-in microphones, software for smartphones that can calibrate to the phone's microphone, or sophisticated software for computers. Most devices can be calibrated, which is needed from time to time. The others will give you a pretty good ballpark measurement though, and they're generally adequate for most gig applications. Calibration is important because varying sensitivities in microphones or gain stage interfaces that are required with software-based solutions will be very inaccurate without it. Take a look at the dB measurements we're seeing on the software without calibration. You can be sure that that's not right. However, with a quick calibration, spot on. When we take measurements, we are likely trying to satisfy a client's specifications or remain in compliance with an ordinance, rule, or law. To do this accurately, we need to be aware of some differences in response averaging and weight scales that need to be applied to these measurements.
Audio peaks up and down a great deal, and it does so very rapidly. If we use a fast response, we'll measure the peaks, but not the real RMS value of the sound being produced. Generally, some form of averaging is expected with a measurement. We can see the difference on this software's real-time analyzer. See how quickly these bars bounce up and down as I talk? Now, if we change the averaging, say to about 1 second, we can see the difference it makes. Additionally, we don't value all measurements the same. There are weighting scales we use to contour the measurement for a specific purpose. The most true measurement is a flat one where no bias is being applied at any frequency. However, humans don't hear all frequencies equally, so when noise ordinances or hearing protection requirements are involved, we generally apply an A weighting, often represented as dBA. This graph shows a negative bias starting at about 500 Hz, a slightly positive bias somewhere in the 2K to 5K range, and a negative bias again beginning around 7K. It's generally accepted that the A weighting most accurately represents the perceived loudness to humans, but it's not a great indicator in a full bandwidth sound system. Right now behind me we have a subwoofer playing pink noise, and we have a meter that's detecting the frequencies it's producing. When I talk, you can see the frequencies in the higher range come out, but when I don't, you can see just the subwoofer's frequencies. You'll note that right now the meter, which is set to a flat weighting, is registering about 95 or 96 dB. When we change this to an A weighting, you'll note that that value drops substantially because of the negative bias the A weighting applies to those lower frequencies. When it comes to hearing protection and noise ordinances, we often see the A scale being referenced. A perfect example is the OSHA standards found in 1910.95, which defines the specifics for computation, instrumentation for measurement, and their respective calibration and exposure levels. We can find the occupational exposure limits in 1910.95's table G16. We'll show you a chart on the screen here in a moment, but this information and more is readily available at www.osha.gov if you're up for a little light reading.
Here are some examples of sound levels that encounter in everyday life. A quiet library is around 40 dB, while the average conversation is around 60 dB. A busy road is around 80 dB, but a diesel truck can be over 90 dB. A rock concert is usually around 100 dB. The humans usually reach a threshold discomfort around 120 dB. Looking at this chart, we can see a few things that should strike us as fairly obvious. As the noise level increases, the allowable exposure decreases. Another thing we should note is that the table calls for a measurement made with an A weighting and a slow or average response. The notable thing for those of us that work in the pro audio industry is that without hearing protection, our day is over in 15 minutes if we're exposed to 115 dBA levels.
You know what, Chris? I want to go around town and see how loud some of the other things in our daily life are.
Let's go!
In our quest to go out and about and see how loud the decibel levels we're going to experience in everyday life are, I've met up with my friend Mitch here, who owns my favorite local restaurant. We decided to see how loud an average lunch crowd was, and so we've got a meter on my smartphone, and it's surprisingly accurate as compared to professional meters, although I think for professional applications, still a good idea to have a commercial model that can be calibrated. But these are pretty good in a pinch. They'll give you a pretty good ballpark idea, and we found that on the A scale with slow response, it's within 1 or 2 dB of being right in there with a calibrated meter. And what we observed here is with Mitch's very energetic lunch crowd, we've got levels in the mid to high 70s on the A scale with slow response. I think one thing we're all pretty familiar with, of course, is cars. And of course, for my job, I spend a lot of time in cars. So I wanted to see how loud it was at highway speeds. And in this truck, we're seeing levels kind of in the high 60s, low 70s. And that measurement, of course, is on the A scale with a slow response. I'm here with Hall of Fame Zamboni driver Vance Balstead because we wanted to know how loud is a Zamboni. We're going to use the A weighting measurements because that's what OSHA is concerned about when it concerns hearing loss. Vance, let's fire this thing up.
You ready to rock?
Let's rock.
Let's rock.
You know what else I was wondering, Vance? How loud is a Zamboni's horn?
Well, I'll just show you, okay?
All right. Well, thanks a lot, Vance. That's a lot of fun. We really appreciate it.
Not a problem, Ben. Anytime. It's my pleasure.
So now you know how loud a Zamboni is. Remember when your parents told you not to listen to loud music? Well, it turns out there's something to it after all. According to Neil Bauman, PhD with the Center for Hearing Loss Help, loss of hearing is maybe not as attributable to presbycusis as once thought. That's a big fancy word to say that hearing loss was simply a product of age and the parts wearing out. Rather, it's becoming more accepted that hearing loss is caused by socioacusis, which is the loss of hearing due to continued exposure to noises in modern society. Therefore, we need to protect our hearing with appropriate safety equipment.
These little foam lifesavers can reduce the SPL by 30 dB, which can mean a difference of many hours in allowable exposure time, and they only cost pennies. It's a no-brainer to protect your hearing.